So this is the fifth chapter of the fourth section of geometry, and this is going to be about one last shortcut specifically for right triangles. So we've gone over side, 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 angle, side, angle, 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 side. Those are the shortcuts we have for proving triangles are congruent. This last one here is going to be specifically for proving right triangles are congruent, so triangles with a right angle in them. So just some vocab first before we get into this. Remember that in a right triangle, we have classify the sides one of two ways. We have the side across the right angle, and that's called the hypotenuse. Hypotenuse. That's the hypotenuse. And then the two sides that are not the hypotenuse are called the legs. So this would be a leg, and this would be a leg. Okay? So the reason we go over this is because the theorem that we have that acts as a shortcut today is called the hypotenuse leg theorem. So obviously we need to know what the hypotenuse and leg mean in a triangle. So hypotenuse is the side across the right angle. Leg is the side that's basically attached to the right angle, or one of the sides that's attached to the right angle. Now there's actually four different shortcuts we have for right triangles. However, most of them are just variations of the other ones we did. The one that's really unique and different is this last one here, hypotenuse leg. So that's the one we're going to be focusing on. And basically it says that if you want to prove two right triangles are congruent, as long as you have the hypotenuse congruent, as long as you have a matching pair of legs congruent, then you can say the entire triangles are congruent themselves. So how does this look as a picture? So, for example, let's say you're trying to prove that these two triangles are congruent. If you could say that the hypotenuses were congruent and say that these two legs were congruent, then that would be a hypotenuse leg case. You could say that they're congruent by hypotenuse leg. Or if you had the hypotenuse congruent and you had these two legs congruent, that would also be a case of hypotenuse leg. So it doesn't matter which set of legs you have congruent as long as you have a set of matching legs congruent in the two triangles. The key there is though you do have to have the hypotenuses congruent. It's not a leg-leg. Technically, if you have a leg-leg congruency, that means you have a side angle side anyway, so you shouldn't need to do that. But basically, this allows us to simply prove two right triangles are congruent by simply using two sides, so like an SS theorem almost, which is why it's so unique and special. But again, it only works if you know that the triangles are both right triangles. So let's practice some of this here. So it says given that AD is perpendicular to BC. So remember this little upside down T here means that these two lines are perpendicular or that they form right angles. And it says that AB is congruent to AC. Prove that the two triangles are congruent. Okay, let's make my two column here. And again, just to save some video time, I'm just going to put given. Okay. Now it says that AD is perpendicular to BC. So that means that AD and BC are going to make right angles, because that's what perpendicular means. So I'm going to put that down right here. BDA angle and angle CDA are, let me erase that. That doesn't look like an A at all. Guys, again. Go. So given. So CDA are right, RT for right angles. So how do I know that angle CDA and angle BDA are right angles? Well, it's because of definition of perpendicular, which is that upside down T. So definition of perpendicular lines. So you want to use the symbol for perpendicular rather than writing out the word. That's just fine. So now I've established that they are right angles. Now I have the option to use hypotenuse leg if I come across it. So you first to make sure that you're either given or that you state that two angles are right angles in the triangles before you use the theorem, because again, the theorem only works if you have right triangles, not just any old triangle. So now that I have the two angles are right angles, the first thing I see is this middle section here, AD. That's acting as a connecting line between the two triangles. That's in both cases, right? Here is AD, here is AD. So I'm going to say that AD is congruent to AD because of our good friend reflexive property. Reflexive. Okay. Because again, if I see that a line is in both triangles, I'm going to mark it as congruent to itself, so it gives me a free side. Now the given also says that AB is congruent to AC. That's given to me. AB is congruent to AC. So now I have a hypotenuse leg situation. I have the two hypotenuses or hypotenuses congruent to each other. So this hypotenuse is congruent to that hypotenuse. And I have that their shared leg is congruent to itself. So now I can go ahead and say that the two triangles, ABD, is congruent to triangle ACD by HL, hypotenuse leg. Okay. So I know that they're both right triangles. I know that the hypotenuses are congruent. I know that they share a leg that's congruent to itself. So HL works in that case. Not the only way I could have done this, by the way, but probably the easiest way of going about it. But again, it was dependent on me getting right angles first. So usually they're given to you, but if they're not given to you, be on the lookout for looking at two things that are perpendicular. Because if you see this word perpendicular or see the symbol for perpendicular, that means there are right angles in there that you can utilize if you want. Let's try another one here. So given the diagram here, so just given the picture, and it's labeled for us, so we know that, for example, these two lines, X and Y, are parallel because they have double arrows. And these two lines, L and M, are parallel because they also have arrows. So that means that they're going to be parallel to each other. So I'm going to say, given. Now, I don't have any perpendicular or right angles here, so I'm going to probably not have the use of HL because there's no right angles to use here, so I can't use hypotenuse leg because there are no right angles to go off of. One thing I do notice here is that both these triangles share a side AC there, right, going down the diagonal there. So this side right here, AC. So I'm going to say that that's congruent to itself first. Because again, if it's a shared piece, might as well use reflexive to give me a free side, right? Reflexive. Okay. Now, I know that the lines are parallel, like X and Y, I know that they are parallel, and L and M, I know that they are parallel. And when I see parallel lines, as I said in the last video, the first thing I go to is looking for alternate interior or corresponding angles. So let me do my Z trick here to see if I can't trace out some alternate angles. So if line X and Y are parallel, that means I'm going to go up line X, okay, and then down the transversal that connects them, and then up line Y. Okay. So I do have my Z there, so that means that I have this angle, this corner of the Z, is congruent to this corner of the Z. So that would be angle BAC. So angle BAC is congruent to angle DCA. So angle DCA. And that's by alternate interior. So alternate interior angles. And then if I try the other lines here, because I have lines L and M also being congruent, right? So let's do this pen here. L and M, if I go down those lines there, so down L, hit the transversal, down M. I also have that this corner angle here is going to be congruent to this corner angle here. Again, the corners of the Z. So DAC and BCA. So angle DAC is congruent to angle BCA, also by alternate interior. So I'm just going to put them in the same box there. So if I take stock of what I have here, come on. If I mark down all the stuff I have congruent so I can start seeing what picture I have and what kind of congruency to use, I have AC congruent to itself. I have this corner angle is congruent to this corner angle. And I have that this corner angle is congruent to this corner angle. So it looks like I have a set of matching angles, a matching side, and then another set of matching angles. And if I try to draw a line between my two A's here, I'm going to cross over my S. So it looks like I have an angle side angle relation. So triangle ABC is congruent triangle CDA by angle, angle, side, angle. Okay? So again, just because you have use of HL doesn't mean you're going to use it every single time. Because obviously if there's no right angles, we can't use it. What about this one? FG is perpendicular. Okay, so perpendicular, that means I have a right angle involved, so HL is on the table. It doesn't mean I have to use it, but it means that it's probably an option I can use if I want. So we have FG is perpendicular bisector too. So bisector means that something's been cut in half as well to EK. So given. So first off, we'll start with the perpendicular aspect. If it's perpendicular to EK, that means that I have two right angles here and here because it's a perpendicular bisector, which means, again, it's perpendicular, mixed right angles. So angle KGF and angle EGF are right angles. And that's by definition of perpendicular. Perpendicular lines, if you want to be specific. Definition of perpendicular lines. And it also is a bisector, right? It says perpendicular bisector. So if it's a bisector, that means that it cuts EK in half, which means that the top half of EK has to be equal to the bottom half. So EG has to be congruent to EK, or not EK, to GK. Why? Well, because that's the definition of bisector. Now, if I wanted to make hypotenuse leg, that means I'd have to get FK and FE congruent. And unfortunately, I don't see a way to say that FK and FE are congruent. They look like they would be, but there's no rationale or reason I can use there. But one thing I haven't done yet that I probably should have done first is I can see a reflexive line, which is that FG, right? FG is that line that's in between both triangles. And again, FG here, FG there. So I'm going to say that FG is congruent to FG by reflexive. Reflexive. Now, I don't have HL, but it does look like I have a side angle side case because I have a set of matching sides. I have the angle between them that's congruent because they're both right angles. And then I have another set of matching sides, which is the shared piece. So I have a side angle side case here, even though I don't have an HL, which is fine. You don't have to use HL. HL is just a shortcut. But if side angle side is going to be easier to use, then let's do that. Technically, though, before I use side angle side, I need to say this. KGF, which is that right angle there, is congruent to angle EGF. Why? Well, because of, I should just say right angle theorem. Right angle theorem. So the right angle theorem says that all right angles are congruent, which sounds like a redundant thing to say because you know that right angles are all equal to 90, and if they're all equal to 90, then of course they have to be equal to each other because they're all the same measurement. But it is something you have to say there. So if I'm going to use side angle side, I can't just leave it as the fact that they're right angles. I have to say that they're also congruent. So that's where the right angle theorem comes into play. So if you have a set of right angles and you decide not to use HL and you want to use something else like side angle side or angle side, so I got a hiccup there, then make sure you include, another hiccup, make sure you include the right angle theorem to say that the angles are congruent. Okay? My apologies for that. So now we can go ahead and say that angle FGE is congruent to angle FGK by side angle side. Okay? And that's that. So just because you have right angles involved does not mean you have to use the right angle or the HL theorem. You can still use side, angle, all that good stuff there if need be. And I think we have one more here. Sorry. So given that A is a midpoint of FB, prove that they're congruent. Prove that FD is congruent to BC. Now, notice here that it's saying prove that FD is congruent to BC, not that two triangles are congruent. So this means that we're probably going to be using a CPCTC case at the end. Because remember, this is what we use to prove that two things are congruent after we've proven that the triangles are congruent. So we're probably going to be on the lookout for that. So let's go ahead and put this as my given. Now, it's not a lot of given, but we can go with it. So if A is a midpoint of FB, that means that FA and AB have to be congruent. Because that's what midpoint means. Midpoint means to cut in half. So the first half, FA, has to be congruent to the second half, AB. So we're going to write that down there. FA is congruent to AB by definition of midpoint. I'm going to put MP here for short just because I don't have a lot of space left. Okay. So that's one pair of sides down. Also in the diagram, even though they don't say it in the given, in the diagram they show us that angle F and angle B are right angles, so we can assume that that's true as well. So anything that's labeled on the diagram pre our work here, we can also say is the given as well. So FB is congruent to, or sorry, angle F is congruent to angle B as well, or that they're both right angles. So I could use HL here if I can get the two hypotenuses congruent, right? So if I can get DA congruent to AC, then I can use HL to say that this triangle is congruent to this triangle. But how do I get these two diagonals congruent to each other? Well, that deals with this middle triangle. So this middle triangle right here is actually isosceles. And how do I know it's isosceles? Well, because these bottom two angles here are congruent. So ADC, this bottom angle right here, and ACD, this bottom angle right here, if those are congruent, that means that the triangle is isosceles with AD being congruent to AC. And that is the isosceles, I'm just going to put ISO for short, isosceles triangle theorem. So the isosceles triangle theorem says if you have the base angles of a triangle congruent, then the two sides are going to be congruent and it's going to be an isosceles triangle. So basically, if you have this, and I say that this is congruent to that, then you know by the isosceles triangle theorem that the two sides opposite them have to be congruent to each other. Or if it was like this, and I said that, okay, this angle here is congruent to this angle here, then I know that this side is congruent to that side. So it can be worked if they're twisted as well. But I know that AD is going to be congruent to AC. And now I can use HL. So now I can say that triangle DFA is going to be congruent to triangle CBA by HL. Now, some of you might stop here, but you don't want to, because the goal wasn't to prove that the triangles are congruent. The goal was to prove that FD is congruent to BC. So now that I have the triangles congruent, I can say that FD, this side right here, is congruent to BC, this side right here, because they're corresponding parts. So FD is congruent to BC because of, as we said on top, CPCTC. Corresponding parts of congruent triangles are congruent. So I've proven the triangles are congruent. I know that FD and BC are corresponding because of their position. Therefore, they have to be congruent as well. So that's it for this video. Again, right now we have 4 shortcuts to do, or 4 basically ideas to go for when we're doing proving triangles congruent. We have the side, 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 prove 3 sides. We have side, angle, side, prove 2 sides and an angle are congruent. We have angle, angle, side. We have angle, side, angle. And then the one specifically for right triangles we have is HL. So when I say prove 2 triangles are congruent, you're looking to get into one of these 5 cases. If you can get into one of these 5 cases, then you can just use that abbreviation to say that the triangles are congruent and then be done with it. Or if you need to prove that 2 angles or sides are congruent, you can finish it off with CPCTC like in this one. But the first and primary goal is to get one of these sets of 5 proving the triangles are congruent regardless. So hopefully you enjoyed the video. Again, please let me know if you have any questions. Keep practicing, keep at it. I know it's going to be a struggle for some of you, which is fine. This stuff is kind of weird for some of you, a different way of thinking, but with practice and effort, you'll get there. So hopefully you enjoyed the video. Have a good day, night, or afternoon.